Hey guys, and welcome back to Chemistry 1032 Instructional Videos. I am your host, Dr. Russell Betts, and I'll be guiding you through the 7.4, Attractive Forces and Solubility. Now, this is a very important concept in chemistry, all right? First of all, there's this thing called the golden rule. Like dissolves like. Write that down. Like dissolves like. Now, basically what that means is that polar things dissolve polar things. Non-polar things dissolve non-polar things. Very simple. For example, water is polar. We know that. So water will dissolve things that are polar, like alcohol, sugar, sodium chloride, table salt. It'll dissolve all these things because those things are polar. They can interact with each other. Now, non-polar things dissolve non-polar things. So let's take, for example, oil, motor oil. Most of us, I hope you haven't, but I'm sure most of us have had our car leak a little oil onto our driveway. And it leaves a nice oil stain on the old driveway. Get out some water, try to clean it, doesn't clean it. Because oil, motor oil, is non-polar. Motor oil is non-polar, so water will not clean it. Water won't dissolve it. Oil and water don't mix. You've heard that saying before, I'm sure. Oil and water don't mix, so they won't dissolve each other. They won't interact with each other. So, to clean oil off your driveway, you need to use a non-polar thing, which is why some people throw some soap in there, because some soap has a non-polar property to it. We'll get to that later. Excuse me. Now, like dissolves like. Oil dissolves oil, water dissolves polar things. Non-polar dissolve non-polar. That's how it works. Okay? It's called the golden rule of chemistry. I always thought the golden rule was do unto others as you would have done unto you. But hey, in chemistry, it's like dissolve like. Now, polar compounds. Here we go. We have some sugar. This is the table sugar right here. Notice how there's alcohols and then there's this O here. Water interacts with sugar very well because sugar is polar. Hydrogen bonds to it. Sugar's polar. Water's polar. They interact with each other. So water can dissolve sugar into it because of the hydrogen bonding. Pretty cool, huh? I mean, that's why it dissolves. Isn't that neat? Here's ionic compounds. Water can dissolve ionic compounds. Not all of them, but a lot of them. And again, it's just because water can surround the ions with charge. Now remember, sodium is positive. It needs to have negative charge around it. Needs to have negative charge all around it. So water will simply surround sodium, facing the delta negative oxygens towards that cation, towards it, giving sodium a negative environment to hang out in, thus stripping it away from its chloride counterparts. Okay? Now this process of the water surrounding the ions is called hydration. Now remember, of course, chloride is negative, right? And we know in water, the hydrogens are positive, or delta positive, right? Okay, so the delta positive hydrogens of water will surround the chlorides, hydrating them. The process is called hydration. Hydrating them, pulling them away from the sodium, giving the chlorides a positive environment to hang out in. And this is why they'll dissolve. Tell me that's not cool. That's pretty interesting, I think. I think that's pretty interesting. I can't pronounce this word, I'm so sorry. Amphipathic compounds. They are compounds that are both polar and non-polar. They have a split personality. Now, great example of an amphipathic compound are fatty acids. Remember fatty acids? So here we have the anion of a fatty acid. This part here is polar, and this part here is nonpolar. So inside of the same molecule, you have both polar and nonpolar groups. You have the polar, what we call the head, and the nonpolar, what we call the tail. And this is where all the carbons are. And this is where the COO minus is. They're called carboxylates. Okay? So there's a split personality. This part wants to associate with water because it's polar. The part down here, this part here, hates water, can't stand it. It's going to get away from it. Okay? Now this is interesting. We have a molecule with a split personality. One part polar, one part nonpolar. One part loves water, one part hates water or fears water. Okay? Keep that in mind. Amphipathic. Now, soap is a great example of an amphipathic compound. All right? Soap. Huh. Well, let's read about this a little bit. Fatty acid salts are ionic because they contain a carboxylate. Let me draw that for you. That's carboxylate. Hydrogen removed from the functional group at one end. So there's your negative charge right there. This is where the hydrogen used to be, is right here. It's gone now. And replaced with a O negative. So this is going to be ionic. This is ionic, guys. Okay. The charge on the carboxylate makes this end of the molecule ionic. In other words, it's going to want to hang out with water. It's going to want to hang out with water. Now they have, fatty acids also have long hydrocarbon tails and extremely polar heads. Okay, here we go. There you go. Extremely long tail. Now this is nonpolar. Again, this is polar. Okay? This is soap. What I've drawn for you right now is soap. Put a little cat eye in here. You got yourself a soap molecule. Oh, isn't that cool? That's soap. That's soap. Now, the nonpolar tails are hydrophobic. Write that word down. Hydrophobic means water fearing and will not associate with water. Period. The ionic heads, we said, were polar, so they're going to be hydrophilic, which means they love water. They want to embrace it and hang out with it. You know, maybe go out to the movies. Okay? This is hydrophilic. They want to associate with water. They love water. Now, if you put an amphipathic compound into water, oh no, what will happen? Those poor hydrocarbon tails, they just don't want to hang out with them anymore. So what do? They seek each other for support. They seek each other for support. Remember, we have these water-loving and water-fearing or hating part. This part right here wants to hang out. Wants to hang out with water. This part over here cannot stand the sight or the sound of water, even the smell. Ugh, hates water. So what's it going to do? Well, if it's forced to be in water, these tails, these non-polar tails, will find each other. They'll find each other because they don't like water. So what will they do? Imagine my fingers are the tails, and we're in water. We're like, oh, I don't like this, I don't like this water. Ah. And then they'll eventually find each other. And they'll start to say, hey, this isn't so bad now. There's no water in here. This is good. We'll throw any water molecule comes in here. We'll work together and throw them out because we're hydrophobic. We fear water. So we hang out with each other. Isn't that what humans do? When we get afraid, we kind of push together with each other, you know, to fight off the imaginary evil or whatever. Isn't that fun? Now, when they do that, when amphipathic compounds do that in water, they bring together the tails to hang out. They exclude the heads. The heads are now facing the outside. So the tails, if you will, the tails, if you will, are all pointing towards one another. Okay? And the heads will be on here, right? They'll be facing the outside, like this. Okay, the purple parts are the heads. Now what's out here? Water. Water's out there. Okay, so the heads are associating with water. Now that's not a very good drawing. Here's a very good drawing. computer generated image. This is a micelle. Now remember, micelles are three-dimensional. They're balls. They're balls of fat encircled with negatively charged heads. Notice the water molecules are associating with the heads. Oops. Get a different color so you can see it. Heads and tails. Okay? Notice in here, there is no water. No H2O. Hell no H2O. All right? So that's the inside of the micelle. It's completely void of water. Now, this is what soap does. This is what soap does in water. Did you ever wonder why we use soap? Why don't we just use water to wash our hands, for example? Why don't we just use water to wash our clothes? Why do we use soap? What's the point of it? Did you ever wonder that? And hopefully you have, and hopefully you realize that if you just wash your hands in water, your hands don't feel clean. They feel a little greasy, a little slimy. You use soap, it doesn't. And that's because soap can wash off the non-polar things on your hands that water can't, right? Same with your clothes. You know, humans and all animals give off oils naturally into their on their skin, and those oils go into your clothes, right? And if you want to get your clothes clean, you got to get rid of those oils, okay? And eventually they'll start to stink if you don't get rid of them. So you use soap to do that because the micelle, this thing right here, has a non-polar area where the tails are. Okay, that's non-polar. But now, wait a minute. Now, when you do your laundry or when you wash your hands, you don't just let the soap sit on your hands, do you? You don't just submerge your hand in soap and water. No, you scrub your hands. You agitate, right? You know, and your washing machine agitates your clothes. It moves them around, swirls them everywhere. That agitation is important for the soap to open and close the micelle, to force the micelle open, and then it closes again. Forces it open, closes again. Okay? And that opening and closing, that forcing the micelles back and forth and round, allows them then to encapsulate any non-polar grease that might be in there, that might be in your clothes or on your hands. And that's kind of how soap works. You have to be able to open and close that micelle. Just open it, close it, open it, close it, so that it can encapsulate or trap the grease. Pretty neat, huh? I bet you never thought about why soap works or how soap works. But this is what chemistry will do for you. It'll make you think about things and be like, I wonder how that works, which I think is extremely cool about chemistry. All right. Now, I basically just explained this all to you. You can read this at your pleasure. But other than that, that's the end of chapter 7.4. So I want to wish you good luck and good chemistry.